In this session, I'm going to talk about the different kinds of statistical tests that we generally use for comparing groups of data, comparing some kind of observations across the groups, and I want to make some kind of conclusions based on the observations across the group. So basically, when we look at them visually, it might appear that there is a difference in the values between the groups. But what is very much important to understand is that difference really significant? Right? It looks different. The two groups are looking different in some aspect, but are they really different? Is there some kind of statistically significant difference that is existing between them? That is what is the content that we are looking at when we talk of a chi-square test or a t-test or for that matter an analysis of variance. Here we are going to look at these kind of tests apart from even the binomial test as well. These are the four major tests that I am looking at in this session. So that is what initially we will look at the chi-square test and execute it in R, interpret it. So my objective for executing a chi-square test is I want to compare the frequencies across the groups. Whether the frequencies are more or less uniform or having some kind of a difference. If I want to compare the proportions across the groups, I would be using a binomial test. If my objective is to compare the means, test whether the means of the groups are really different or not, then I would be engaging a t-test. And if I want to compare the means across multiple groups, then I would be using ANOVA. So these are the four kinds of tests that I want to look at in this particular session today. So initially getting started with the chi-square test. Of course, first let's look at the conceptual aspect of it. Then we'll put that for a data and then take it up in R as well. So the major point that is getting looked at when I'm talking of a chi-square test is primarily to determine whether the differences that we observe between the groups are they real or is it just because of some kind of sampling error, otherwise called as some kind of minor variation that is present in the data, which means whatever are the differences that you are observing across the group. The intention of any statistical test per se is whether the differences that we are observing across the groups on some variables, are they real or are they primarily because of some kind of minor variation that is present in the data. So coming to this chi-square test, it primarily looks at the frequencies. So the main objective of a chi-square test is it verifies or determines whether the frequencies of different groups are significantly different from what we expect. Whether the actual frequencies of the groups is completely different from the expected frequencies of each of those groups based on their total actual count. So that is what is the major objective of a chi-square test. And this chi-square test always works on a table, right? The table from the raw data, we will make a frequency table out of it, and the chi-square test works on a frequency table. So whenever we are using a chi-square test, or for that matter any of the tests, the first step is I have to create a null and an alternative hypothesis. The null hypothesis says the factors are unrelated. In case of chi-square test, I want to really verify whether the values are significantly different or not. So they are not different, they are unrelated. If I am comparing two factors, then I say that the factors are unrelated is the null hypothesis. So when I am using the word unrelated, the count, the actuals are more or less similar to expected. The actual frequencies are nowhere different from expected. That is what is the major null hypothesis that goes. And what the alternate hypothesis says is no, that is not the case. The actual frequencies are significantly different from that of the expected frequencies. That's the major thing that we have to establish first, right? We have to simply establish the null hypothesis and alternative hypothesis. In case of chi-square test, the null hypothesis simply says there is no relationship between the factors, which is in other way putting it is the actual frequencies of the data will be more or less similar to the expected frequencies. Whereas the alternative hypothesis says no, that is not the case. The actual frequencies are significantly different from the expected frequencies. So that is what we are trying to test using a chi-square test, right? From the chi-square test, we'll take a data. We'll take a quick look at the chi-square test from our data, and based on that, we can make our relevant interpretation. So let me pull in the data again, similar data that we have used earlier. So I'll use the customer segment data itself, right? I'll use the customer segment data itself. So okay, I have to put a double quote here. Yeah, I'll use the customer segment data, which I have used even for visualization stuff as well. So just to recollect what is there, I'll take a head of that customer segment data so that we can understand, oh, these are the segments that are there. So what I can typically look at is, I want to simply perform a chi-square test, let's say on one of the variables. Now, whenever we are taking the chi-square test by default, first thing is I require a table. So let's say I want to go with a table of customer underscore segment dollar, let's say subscribe. I want to see whether there is a significant difference with respect to the subscribers. So it says subscription no is this much, subscription S is this much. On the top of it, I want to use a chi-square test. So I'll say chi-square dot chi-sq dot test. I'll do this table. I'll give this table as an input into this chi-square test. So here I could see some of the important numbers. Let me note them. Chi-square value. The chi-squared value is being given as 161.33. The degrees of freedom is being given as 1, and p-value is being shown as 2.2 into 10 to the power of minus 60. So these are the values that are being produced by my chi-square test. So like this you can do it for almost any kind of qualitative categorical variable. Let's say I want to do the same for segment. So in this case, I got a chi-square value of 17.33. We'll interpret that. The degrees of freedom is coming out as 3, and p-value has come out as 0.006035. So these are the things that are coming out. Now, here, if I look at this simple interpretation, we are talking of the null hypothesis is the proportions are more or less equal. Actual, when I say actual is more similar to expected, it means that proportions across the groups will be more or less equal. So if I have 300 customers data and there are two segments, which are sorry, two categories as a part of subscribe, then I expect 150 and 150 in both of them. But in reality, it is 260 and 40, right? That is the actual value in this case. Whereas in this case, there are four segments, 300 people. So I expect in each segment the number of customers to be around 75. That is the default setting. Expected values are that, but the actuals could be something different. Now, based on that, whether the actuals are more or less similar to that of expected, or are they quite drastically deviating from expected, is what is typically being performed by the chi-square test. So when I give one single input, that is what it takes. It takes a uniform association, uniform proportions across. Now, if I have to evaluate it, I check for the p-value. The p-value in this case is 2.2 into 10 to the power of minus 16. In this case, it is 0.0006. The first thing I will check is p-value, is it less than the significance level that I am setting. In general, we set it at a 5% significance level. If the p-value is less than 5%, my decision will go in favor of alternate hypothesis. If it is greater than 5%, then I cannot go with the alternate hypothesis. I will have to go with the null hypothesis only. Now, in this case, it is 10 to the power of minus 16, which is much less than 0.05. Even in this case, it is less than 0.05, which means I am rejecting the null hypothesis in both the cases. If the p-value comes out to be much higher, then I cannot reject my null hypothesis. But if the p-value is much lesser, I can very well reject my null hypothesis and take my decision in favor of the alternate hypothesis. So in this case, I can take my decision in favor of alternate hypothesis, saying the observations are not uniformly distributed across the subscriptions. They are not uniformly distributed across the different segments as well. The same way, instead of one column, I can take two columns as well. Probably it's as good as saying I'll take a table of the segment along with I will also bring in gender. So gender wise segmentation. So here it's as good as saying if I don't take the chi-square test, only the table. First let me see the gender wise table. This is the gender wise table. Moving up 4921, suburban 4852. So this is the mix gender wise. Now what this chi-square test here is making an assumption or the hypothesis in this case when I am taking two categories. The null hypothesis says the proportions are more or less uniform. So proportion of the customer segments is more or less uniform across the genders. So there is no influence of gender in the proportions of the various segments. Whereas alternate hypothesis says no, there is a difference in the proportion of the segments across the genders. Probably in some segment the proportions of females is much higher. In some segment the proportions of males is much higher. That is what is my alternate hypothesis. So based on that I am looking at my chi-square test. The chi-squared value is 12.734. We don't need to compute it, right? But just to give you the way you are computing it is observed value minus expected value whole squared divided by the expected value. You sum all of them, this would follow a chi-square distribution. This is what we are going to get as the chi-squared value. But in this case, the expected will be coming out as the row total multiplied by the column total divided by the complete total, grand total. That is what will give me the expected value for each aspect of the table. So this is my row totals. I'll have my column totals and this is the total. So this is what will give us the expected values. Based on that, the chi-square is computed 12.734. The degrees of freedom is 3, which is computed as row minus 1, number of rows minus 1 into number of columns minus 1. Here we had 4 rows of data, right? So 4 minus 1 is 3, 2 columns of data, 3 minus 1 is 1. So giving me 3 as the degrees of freedom. Here the p-value is saying 0.005, right? 248, which is less than 0.05. So my decision goes in favor of the alternate hypothesis. The alternate hypothesis says that there is a significant difference in the proportions of the segments across the males and the females. So gender wise there is a difference in the proportion. So this is what we are going with, the p-value and the interpretations based on the p-value. And if at all I am going for a 2 by 2 tables, right, let me go for a 2 by 2 table where gender is a 2 by 2 anyhow. Let me take own home, right? Let me take own home as another variable. This is a 2 by 2 table. Now I execute a chi-square test on the top of the 2 by 2 table. So in this case, I get, okay, you see here, test with its correction. There is a its continuity correction that is applied by default, especially for 2 by 2 tables. Here the chi-square is saying 0.156, right, whereas the p-value is 0.6921, which is greater than 0.05. So I cannot go with the alternate hypothesis. I cannot reject the null hypothesis. So the only thing for me is I have to say that there is no significant difference in the ownership layers across males and females. The proportions of males and females with respect to the various genders is, sorry, the proportions of males and females across the ownerships is more or less similar. So that is where I cannot reject the null hypothesis. Yates correction is also being performed because there is a kind of assumption that the continuous data is imperfect when it comes from a lumpy binomial distribution. It's only a 2 by 2, which means it's a binomial distribution. So whereas the chi-square is a continuous distribution. So especially when the data is coming only from two groups, the kind of assumption relating to the continuous data that I make would be more and more imperfect. So that's where we do some kind of a continuity correction before we really take the data for the computation of the chi-square analysis, right? Then the next important test that I am looking at in this context is the binomial distribution or the binomial test. This binomial test typically is being used when I am going for testing the proportions of the success or proportions of the failure. So that is where the binomial test contains the number of successes in number of trials. So actual number of times an experiment is performed, number of successes that were achieved, and the expected probability that we are looking at for success, the probability of success. Based on that, the binomial test will be conducted. Again, it is testing the likelihood of the this particular number of successes coming in this particular number of trials. So we could take the data. So simply put, if I am saying there is a 50%, so I really want to check whether the probability of success is 50%. Right? I want to check the probability of success is equal to 50%. And then I have conducted a trial 20 times, and let's say the number of successes are 12. Then what is that I can do? I can do a simple binom test. So number of successes is 12, number of trials is 20, and I am checking whether the probability of success is 0.5. So this is what we call as the exact binomial test. Data is 12 and 20, 12 successes out of 20 trials. The p-value is coming out as 0.5034. That is what is the p-value here, which is greater than 0.05. Now in this case, the alternate hypothesis is saying the true probability of success is not equal to 0.5. So the null hypothesis is, in this case, the null hypothesis is the probability of success is 0.05. Sorry, 0.5, 50%. Whereas the alternate hypothesis says no, the probability of success is not 0.5, it's either greater than 0.5 or lower than 0.5. Now this is where we have conducted a binomial test, and the p-value, which is the p-value has typically come out as 0.5034. I have to always compare it with 5%. Greater than that, so I have to go take my decision in favor of the null hypothesis. So wherever my p-value is greater than 0.05, my decision will be in favor of null hypothesis. Wherever the p-value is less than 0.05, then I would reject the null hypothesis and take a decision in favor of the alternate hypothesis. So I will check the likelihood of whether this particular number of successes that are coming in a particular number of trials can be more or less taken as equal to probability of success of 50%. So I am testing the likelihood of that through that, and I am also checking the 95% confidence interval for it. 95% confidence interval is showing 36% to 80%. So there is a chance that the probability of success will be anywhere between 36% to 80%. Now the 50% is within this interval, so that's where we go with the null hypothesis. But if we are talking of 20% as the probability of success, then probably I would have got a p-value less than 0.05, and I would have rejected the null hypothesis as well. So I really want to check whether the 95% confidence interval includes the probability or not. If it includes, then I will not reject the null hypothesis. If the confidence interval does not include the probability of success, then I will reject the null hypothesis and make my decision in favor of the alternate. The same logic goes with the p-value. If the p-value is less than 0.05, I'll make my decision in favor of the alternate hypothesis. If the p is greater than 0.05, I'll make my decision in favor of the null hypothesis itself. Then looking at the 95% confidence interval. So the definition is very important. When I am saying any confidence interval, it is the range of possible estimates, 36% to 80%. We would expect to see 95% of the times. So 95% of the time, the probability of success would be anywhere between 36% to 80%. Only in 5% of the cases, the probability of success can be below 36% or it can be above 80%. So that is what it means. If you have a success of, if you had 12 successes out of 20 trials, the probability of success could be anywhere between 36% to 80%. And there is a 95% chance that it will be between 36% and 80%. If we repeatedly estimate using the random samples of the same size, right? If I say, right, today I have used 20 trials and out of them 12 were success. Tomorrow I again do another 20 trials. Again, let me see some kind of successes. Again the same. Again the same. If I continue this process, for this kind of a person, I can very well say that the number would be anywhere, the probability of success could be anywhere between 36 and 80% with the 95% of the times, but only in the 5%, the probability of success can go either below this or above this. So under the assumption that the true value in an infinitely or very large population is the same as our current estimate. So making that kind of an assumption, we can say that this is the 95% confidence interval which is surrounding our estimate. Or a common man's usage of this confidence interval, probably this is much easier for you to understand. It's a best guess. It's a best guess of the range of the possible answers. When you repeat this experiment n number of times, the probability of success you will get anywhere between 36% to 80%. That's the best guess I can give once by observing one single series of trials. So this has nothing to do with how confident are we within the answer. If the same experiment is repeated so many times, there is a good chance that the probability of success could be anywhere between 36% to 80%. But sometimes people talk about how confident we are in the answer. It has nothing to do with this. It has no input that it has captured which can talk about the degree of confidence. So look at that confidence interval is always about the estimates. It has nothing to do with the true value. We are giving a range in which the true value can lie. We are giving a range of estimate and the true value, whatever is that one single value, we are saying it can lie within this particular range only. So it is not at all talking of the practical importance, meaningfulness of the result. It's purely a statistical stuff. But few important points for us to understand is before making any kind of interpretation of any result, we have to ensure that it is statistically significant, means the p-value is less than 0.05. Ensure that it is statistically significant. So if I am going with a 95% confidence interval, then I will ensure that it is less than 0.05. If I am going with 99% confidence level, then I will check if the p-value is less than 0.01. Only if the result is significant, then only we are proceeding with our interpretations and reportings. So that's also we need to look at, right? Any test that is being performed, first look at the significance level, which is the p-value. If it is less than 0.05, then only we are making it that it is statistically significant, and that statistical significance is what is we are taking forward for any kind of interpretations and reportings. So p-value is less than 0.05. That itself means the differences are statistically significant. Either whatever is the actual probabilities that we have got, they are different from whatever you have hypothesized kind of probability. 50% is what we have hypothesized. So if it is completely different from that, or is it more or less uniform? And in some cases, I can even add up all the probabilities through the d binom function, which is the density estimate of a binomial function, I can do the summations across. Let's say I want to know what is the probability of getting 8 successes, 9 successes, 10 successes, 11, 12 when you are performing a trial of 20 and looking at it as a probability of success of 0.5. In that case, I can do a simple summation wherein I am doing the d binom, which is the density function of binomial. Number of successes, I can take them as a sequence from 8 to 12. Number of trials is 20. The probability of success I'll take as 0.5. Suddenly it gives me that, which is like the probability of getting 8 successes plus probability of getting 9 successes plus probability of getting 10 successes, 11, 12. All these 5 are typically added up to give me this 73 kind of a number. So that's in some cases, if I want to find out the probabilities of various different kinds of successes, I can still use this kind of a mechanism. And in the same way, if I don't do a d binom, if I don't do a sum and just leave it to d binom, I get the probabilities of success of each of the individual stuff. So the probability of success with 8 successes, the 8 out of 20 being successful, what is the probability? What is the probability that 9 out of 20 are successful, 10 out of 20 are successful, 11, 12 out of 20 are successful? So this is what a binomial distribution can typically do. In some cases, the binomial test is overly conservative, especially when I am going with the confidence intervals estimate, the 36% to 80% that we have got earlier. That's a kind of a conservative kind of an estimate. So this is where there is a specific package which is targeted towards a binomial distribution, which is called as the binom package. The binom package has so many features, so many functions, but out of that, the confidence interval function, where it takes the AC method, Agresti-Cole method. That's a kind of an algorithm which is a different way of computing the confidence interval. So getting into that particular method, we can get the confidence interval slightly in a different manner. So you could see here, if I am saying I have to install this package binom, okay, let me install this package called binom. So this is the package. Once it installs, I can load it. So now that it is installed, I can load this package, right? Now in this package, I was talking of binom.conf int. So let me use binom.conf int kind of a function, wherein I'm more interested in finding out how many, if I'm having 12 successes out of 20 trials, and I want to find out the confidence interval, where the method I'm using is the Agresti-Cole method. So I'm setting it as AC. Now this is saying the interval is slightly different, 38.60% to 78.17%, whereas in our earlier case we got it as 36% to 80%, slightly conservative kind of an estimate earlier. But AC method is slightly less conservative. So the confidence interval is slightly smaller compared to what you get in a typical binomial computation. Right, so this is also a kind of an improvised method, and especially the binom package, when you look at many other tests are also there, you can very well explore that package more and more in depth, especially when you are doing a lot of binomial related tests. But on the other side, especially if I want to do the confidence intervals for 0% or 100% kind of stuff, probably your binom.test, let's execute binom.test, where you have 0 successes out of 20 trials, right? And I'm looking at p-value of 0.5. So you say that probability of success is this much, 95% confidence interval is coming out to 0 to 0.16. But if I do the same using this method, I get it as minus 0.02 to 0.18. So minus 0.2, if I can ignore also, I am getting it as 0 to 0.18 kind of an interval. And this is so this is how I get a different confidence intervals when I'm using the Agresti-Cole method, especially when we are going with 0% or 100% of the observations. Then probably the Agresti-Cole method is much appropriate compared to your typical regular binomial distribution kind of method, right? Now, moving on to the next part, where I want to look at comparing the means across the different groups. And when I have to compare the mean values across two or more groups, we are engaging a t-test. So one sample of data, I'm taking the mean, I'm comparing it against the other sample's mean. So probably if I'm talking about the income levels as a comparison, so I take the data of males, I take the data of females, and I try to see if the mean income level of males is significantly different from the mean income level of the females. So we are using this t-test exactly for comparing two sets of data. If I have multiple sets, then probably I cannot use the t-test. I'll talk about it in the next slide, wherein I have to use the ANOVA. So when I'm talking about the t-test now, the intention here is I'm trying to compare one quantitative variable, the means of that particular quantitative variable across two groups of data. But of course, before we execute the entire t-test, which can be executed through this simple formula t.test, I have to examine the data, check if there is some level of skewness present in the data, if there are outliers in the data, and if at all they are present, I have to have some kind of corrections to the data, or I have to get into some kind of transformations on the data. So which will help me to make my data more and more closer to normal. The t-test actually assumes that my data follows a normal distribution. So if at all I have to use the t-test, I have to make sure that my data is following a normal distribution. In that case, if my data is close to normal, then I can very well compare the mean of one sample of data against the other sample. If the skewness is present in the data, if the outliers are present in the data, then my data will no more be closer to normal, which means it might be leading to a completely inaccurate test. Even if I am using the t-test, there may not be any kind of an advantage going with this test. So if I really want to see if the data is close to normal or not normal, I can go for a box plot, see if the level of outliers that are present are significantly higher. Or I can very well use the psych package which we have used earlier, and I can use the describe command as a part of that psych package, which also gives me the skewness associated with the data. So let's say here we'll look at the income levels first, right? So I want to look at the income from the same data. So let me use the psych package first, library psych. So within this package, I'm trying to load the describe function, right? Customer segment dollar income. So here I could see that, okay, this, apart from all these things, the skewness is 0.14. So the skewness should be as much closer to 0 as possible if the data is close to symmetric. Very much negative, then it is negatively skewed. Very much positive, it is positively skewed. Positively skewed means more outliers are present on the right side. Negatively skewed means more outliers are present on the left side. And just as a quick thing, though there are tests to ensure or to test whether the data is normal or not, but as a quick ballpark figure, I can say that as long as my skewness is lying between minus 0.5 to plus zero point 0.5, I can just take it at a periphery level that my data is close and closer to the normal. So in this case, the skewness is looking out to be a 0.14. So I can very well look at the skewness being pretty much closer to normal. But if I really want to see subgroup wise also, not just the group as a whole, but within the income, I want to take a subset where I'm talking of people who own a home is yes. Only for those people who own a home, I really want to check what is the level of skewness. What has happened? There are a few NAs coming up. Why is it so? So let me just check my data. So we'll look at the summary. Obviously there are no NAs. Okay, I have to put double equal to when I did own S, own home equal to own S, own home. Okay, I have to give customer, I have to mention the data frame name, customer segment dollar own home, right? So when you are looking at the distribution of the income for those people who own a home, the skewness is 0.23, again very much closer to 0. And if I look at for those people who do not own a home also, the skewness is minus 0.07, which is again very much close to 0. So I can very well assume that the income levels are more or less normal, both at an aggregate level and even at a subdivision kind of a level. Now this I can either use using the describe package like this, wherein I can compute the skewness levels, or I can very well go for a box plot. Right, I can very well go for a box plot or a histogram kind of stuff. So let's say box plot, the same thing. If I want to look at for the people who own a home, I look at the box plot. I see a few outliers this side, but they are not too significantly far away, right? They are very much closer to this kind of a line. So I can quickly check out the presence of the outliers by using this box plot, or I can very well use that describe command. But even more, if I have to go with a statistical test for ensuring the normality of the data, I have a test called Shapiro.test. I have a test called Shapiro.test which checks for the normality of the data. And the base assumption that it makes is the null hypothesis is the data is normal, whereas the alternate hypothesis says it is not normal. That is what is the Shapiro test. It's called as a Shapiro-Wilk test. So it checks whether my data is normal or not. It's a statistical way of testing it. So you could see the p-value here is less than 0.05. So I would definitely take my decision in favor of the alternate hypothesis, and I can say that this data is not normal, though theoretically I saw the number as 0.23. But if I go strictly in terms of ensuring the normality of the data, it is coming out that this data is typically not normal. So we need to do some kind of transformations and all that stuff. In case probably we have talked of earlier the box Cox kind of a transformation which we have to do. If at all I have to make my data as much closer to normal as possible, right? So I can do that entire transformation, and once my data is ensured to be close to normal, this is where I can perform a t-test. So if you look at the way the t-test is performed, there is a formula and the data. So the formula is nothing but, there's a formula wise I am just setting the dependent variable, which is the response variable versus the grouping variable. So I can take, right, I can take the t-test, t.test, okay, t.test, and on the top of it I'm looking at the income across, let's say, gender. So this is the one I am trying to do, wherein I am taking the data equal to cust underscore seg. I am taking the entire data. On the top of that, I am looking at the I'm looking at income across the gender. So the null hypothesis here is the average income across males is same as average income of females, whereas the alternate hypothesis says no, they are not equal, they are different. So this is what has to be established before the beginning of any particular test. So this is what we are trying to test. Okay, the data is, so this is Welch 2 sample t-test. Data is income by gender. These are all the calculations that went in, but what I am more important, what I am more interested is the p-value 0.08436, which is greater than 0.05. So my decision is always in favor of null hypothesis. So here I will say that the mean income levels of males is more or less similar to the mean income levels of the female. There is no statistically significant difference in the income levels of males versus the females. The same thing, okay, instead of looking at gender, I want to look at own home. For people who own a home versus people who don't own a home, is there any difference in the income levels? So here the p-value is saying it is 0.001, which is less than 0.05. So my decision is in favor of the alternate hypothesis, saying that there is a difference in the income levels between people who own a home versus who don't own a home. So for people who own a home, the mean is around 47,000. For people who own a home, the mean is around 54,000. So I can clearly make a statement that people who own a home have higher income levels compared to people who don't own a home. That is how we are interpreting the t-test. So we have a formula. There is a response variable tilde the grouping variable. Output wise, I look at the t statistic and the p value. T statistic is just an intermediate computation. P value is what we are using for decision purpose. P value less than 0.05, my decision will be in favor of alternate hypothesis. P value greater than 0.05, my decision will be in the favor of null hypothesis. So null hypothesis of no difference is either rejected or failed to be rejected. If P is less than 0.05, I'll go for rejecting the null. If it is greater than 0.05, I do not reject the null hypothesis. Then I'll also be looking at the 95% confidence interval of the difference. So the difference between the two means can be anywhere between minus 12,000 to minus 3,000. So that's the level of difference that can exist in the means of both the groups. So if the difference contains a 0, then I will not reject the null hypothesis. If the difference does not contain a 0, I can reject the null hypothesis. That's also another way of making an interpretation by looking at this test. If that confidence interval difference contains a 0, I will not reject the null hypothesis. If it does not contain a 0, I will reject the null hypothesis. Then it also gives me the sample means for our data. In some cases, I may not look at the whole data also. In some cases, I may want to do it on a subset of data. Right? Let's say instead of taking the whole data of customer segment, let's say I want to take only only the males. So I'll say subset, right? I'm taking a subset of the customer segment, right? I'm taking the subset of the customer segment wherein the gender equal to male. I'm simply setting the gender equal to male. So in that case, there is again a different test that is performed. P value is 0.005 less than 0.05. So I'll go with the alternate hypothesis. So even in terms of males, people who own a home, the income of people who own a home is different from the income of the people who do not own a home. For people who own a home, the mean is around 54,169. But for those who don't own a home, it's around 44,371. So you can very well take either the full data or you can go with a subset of data, but we need to know how to interpret the output that is coming out of the t-test. But remember, this entire t-test makes a lot of sense only when we are using two groups. But when multiple groups are existing, let's say across the four customer segments, that I want to compare the means. In that case, the t-test does not work well. I have to do multiple t-tests or a much more robust procedure called ANOVA we have to engage. ANOVA is analysis of variance, and that is what I can engage in case there are multiple groups across which the means required to be compared. So in the next topic, we are going to look at ANOVA in more depth. All right. Moving to the next topic in this context, where I'm trying to look at comparing the means across multiple groups. I'm using the concept of ANOVA. So the way it compares, it takes two things: the means between the groups versus the means within the group. So it looks at the degree to which the groups differ. So it takes the kind of variation that is existing between the groups. It also looks at the kind of variance that is existing within the groups. So this is what is ANOVA. That's the reason the variance analysis of variance has come up. So it looks at variance in the means from each other. So if I'm looking at group 1, group 2, group 3, it looks at the variance in the means from each other versus the variance of the observations within each of the groups. And when I'm talking of group here, it could be based on one single factor, in which case it is called as one-way ANOVA. Two factors, it could be called as two-way ANOVA, multi-factor ANOVA, or it can even bring in different kinds of interactions among the factors. Right? It's just like factor 1, factor 2 individually, and along with that the combined effect of factor 1 and factor 2. So even those kind of things can be handled as a part of ANOVA. We have two steps when we are talking of ANOVA model in R. First thing is we are using AOV, wherein I am giving the formula where I am talking about a response variable versus a grouping variable. This is primarily used to set up the model. Now in this, the kind of grouping variables that I can add, I can keep them as it is. If I just want to add their main effects variables independently, then I'll put a plus sign. If I want to talk about the interaction between them, then I'll use a star. And if I want, sorry, for an interaction, I'll be using a colon. And if I'm looking at both main effect as well as the interaction effect between the variables, then I'll be using a star. So this AOV is what will set up the model. And regarding the analysis or the summary of the model, I'll use a formula called ANOVA and that model name that I'm giving. So a standard ANOVA summary comes out, which I should be comfortable in terms of interpreting. So let me execute this ANOVA, right? So we'll take two or more groups of data. So let me do it the income across segments, right? So that's the reason we will call AOV first of all, where I'll say income tilde segment. I'm looking at income across the segments where my data is cust underscore seg. This is my ANOVA model. It's better that I save this particular model to a particular variable because anyhow I have to do an ANOVA on the top of it to compare to get the complete ANOVA table. So let me call this entire thing income versus segment. So income underscore segment underscore comparison, right? Let me call it like this: income underscore segment SEG underscore comparison. So that's what I'm calling as INC, and I'll put an ANOVA on the top of this variable. So I'll do an ANOVA of this particular variable. So this is what we call as the standard ANOVA table, right? So the degrees of freedom, segment versus the residuals, sum of squares, segment versus the residuals, mean squares of the segment versus the residuals, f value and the probability of greater than f. So this is the typical ANOVA table that comes out. First thing that is important for us as an analysis, or probably first let me set the null hypothesis in case of ANOVA is the means of incomes across all the groups is more or less equal. Mean of G1 equal to mean of G2 equal to mean of G3 equal to G4. The mean value across all the groups is uniform. And the alternate hypothesis says at least across one of the groups there exists a difference. So that when I am executing it and looking at the output, the probability of greater than f, the value is very important. Here it is showing 2.2 into 10 to the power of minus 16. This is what is actually the p value. So this less than 0.05, my decision will go in terms of alternate hypothesis. The alternate hypothesis says no, the means across the groups are not equal. So there is a significant variation. In this case, I can say there is a significant variation in the dependent variable, which is the income, between the various groups that I have considered. So there is a significant variation in the income levels across the different segments that we have considered. The same logic, now I can pull in two groups, right? I mean, if I say this is called one way ANOVA or one factor ANOVA, but let's say along with this, I would also try to bring in one more variable, right? Instead of just saying segment alone, let me also add the own home. I'm looking at the income levels across the segment along with own home. So here it will have two individual variables impacting. Segment separately, owning a home separately. And let me do an ANOVA this time on the variable. This time the ANOVA is coming out as, here it shows segment, own home, residuals. And for the segment it is giving me a p-value 2.2 into less than 2 into 10 to the power of minus 16. But for own home, the probability or the p-value is 0.57, which is greater than 0.05, which means own home is not at all influencing the dependent variable, which is income. There is no difference in the income. But if you look at own home only, another model let me take. Let me not consider the segment at all. Let me just take income versus own home. And if I take the ANOVA of that, right, income versus the own home, if I take the ANOVA of that, the p-value is 0.001, less than 0.05, which means separately there is a difference in income. There is a significant difference in income for people who own a home versus do not own a home. Similarly, there is a difference in the income between the people who are belonging to the four different segments. So income is significantly different across this, income is significantly different across this. But let's say I want to club both of them, right? I want to club both of them, and that is where I have done the earlier part. This particular thing where I have clubbed both of them to see which one is more important out of the two, or are both of them equally contributing. So that is where I have joined them with a plus sign. I could see that when I did it, only the segment is coming more and more significant, but own home is not coming much significant. So whatever is the difference that is coming out because of the own home is already taken care of as a part of the segment. So now own home is not contributing separately in any way, contributing to the differentials in the income across the group. So that is what I mean by this statement. Individually the variables may be significantly differentiating. When I looked at income versus own home, I got that the differences are significant. When I looked at the income versus the different customer segments, I got they are different. But when I combined both of them, it looked as if the uh, the income is significantly influenced or differentiated by the segments only, but not by the status of owning the home. Because the two variables that I have considered there, they need not be independent. They may have a lot of interdependency between them. Because of that, one was sufficient to explain the difference in the income. The second one was not needed at all. And in some cases, the model could be slightly improvised in terms of saying not a plus, but I have put a star to see the interaction effect between the segment and owning a home. Right? In some cases, even such kind of thing is also being considered. So if there is an interaction effect, when I put a star, I'll get both the main effects as well as the interaction effects between the variable. Now in this case, you could see here the segment, this is the p-value, less than 0.05. Own home, this is the p-value, and the interaction, this is the p-value. So neither the interaction nor the own home are creating any kind of difference with respect to our income variable. It's only a segment which is a differentiator, strong differentiator of income across the independent variable, across the income as a variable. So I can say that the income is varying significantly across the different segments, but not that influenced by the owning home or a combination effect of the two. So that's how we make our conclusions based on ANOVA. And in some cases, if I have multiple models created, of course here I had created multiple models, but all of them I have created with the same name. So let's say I look at this as one model which has owning a home along with interaction effect, and let me call that as one model, INC segment comp. Then I'll take another called as INC segment comp 1, where I'll take only segment. I'll not take one home at all, which we have already done. I'll take only the segment as the variable, finding the difference in the income across the segments. And from this, I can very well do an ANOVA of the comp 1, this one. Now this is also showing a p-value less than 0.05. So segment is definitely influencing the income. There is a difference in the income across the segment. Now out of these two models, INC segment comparison, income segment comparison and income segment comparison 1, if I want to compare whether these two they are significantly different or they are not, then also I can give ANOVA. I can do an ANOVA wherein I can give these two inputs. Okay, I'm comparing this model versus this model. So comp 1 is primarily only segment, whereas comp 2 I am looking at segment versus owning a home and their interaction effect as well. Now, this is what is the summary. Model 1 is income versus segment multiplied by own home, which means segment separately, own home separately, and the interaction effect between segment and own home. Model 2 is looking at income, how it differences across the segments. Now, here there are few outputs that are coming up, but more importantly, it is the p-value. The p-value is 0.83 greater than 0.05. So I cannot reject the null hypothesis. I have to go with the null hypothesis, and null hypothesis says no significant difference between the models. There is really no significant difference between the models. Means adding a own home as the additional variable in terms of bifurcating the income or even the interaction effect between the income and the segment is not creating any kind of influence on the income. So this is how we can do the model comparisons as well. Especially if I have nested models only, I can do this kind of comparison. When I use nested models here, it means that I'm adding one more additional variable, two more additional variable. If I take this, income segment comp, there were two variables, segment and own home, and the interaction between them. If I remove the own home from it, it is just a segment. So one set of variables should be a subset of the other set of variables. In that case, we call the models as nested. This kind of ANOVA comparison is more and more appropriate only when I am looking at nested models. But in general, if I have to compare the models, let's say I create one model of income versus gender and the other model of income versus segment. I can't compare these two things. Yeah, I mean, though ANOVA will give me some kind of an output in R, but there is no meaning to the interpretation part of it. So if I have one model as income versus gender, another model as income versus gender plus or star own home, then I can very well call them as nested models, because by removing one or two variables from one model, the other model can be derived. But in general, if I have to do the comparisons across two different models like this, we have to use some kind of criteria wherever at a later point when we come across, we'll be using them. We'll be using the criteria which you can call it as equivalent to that of an error function. So Akaike information criteria or Bayesian information criteria kind of things are typically used, based on which the multiple models can quite comfortably be compared. Then the next thing that I am looking at is the confidence intervals between the groups. Right now we have seen here that there is a difference in the income levels across the segment. Now I want to really visualize what are the confidence intervals across the groups. I want to visualize them. So which talks about whether the differences between the groups are substantial in magnitude or not. So I have a package here, multcom package, which can do this kind of work for us. So let's install this multcom package. Which will do a multi-model comparison. So let me load the multcom package. Now what this multcom package does is, I'll first compute. Let's look at this. The multcom package, it has a function called GLHT, General Linear Hypothesis. General Linear Hypothesis command. So I have to give an AOV object. I'll compute an AOV and inspect it with GLHT. So let me say we have already an AOV object. So let me bring that. Right. So let me take this inc underscore seg underscore comp1. This is we have used the AOV function on the top of it. So I want to use this as an input to my GLHT. Right. I'll take a GLHT function which is doing the comparison of the confidence intervals across the groups. So this is what is the comparison of the confidence intervals. Of course, here there is an intercept part and only 3 groups are being considered. The 4th group is being considered as a part of the intercept. But rather than that, if I want to keep all the 4 groups as a part of the model, then remove the intercept from the model. So which means when I am computing INC comp1, I will instead of just saying segment, I will set -1 plus segment. -1 itself indicates that I don't want the intercept part. So when I say -1 plus segment, it means I don't want the intercept part. So this is my new ANOVA model that is getting created. That is what I'll give as an input to my GLHT. So now it says these are the values. Segment moving up equal to 0. The estimate is 53,000. Segment suburban mix equal to 0 is 55,000. Similarly 62,000 and 21,000. So I am getting the mean of each one of them, and probably I can very well get the plot of this GLHT object. Whatever is the GLHT object that I have, I can create the plot of this entire thing. This is how the plot is coming up. The moving up, this is the range. Suburban mix, this is the range. Travelers, this is the range. Whereas the urban hip is coming out in this range. It looks as if these 3 intervals are more or less overlapping, but only this one is looking wide away from the rest. But here the margins are typically going off, right? So this is where I can even adjust the margins by using my par function. So I can set par margins. I can set, okay, on 4 directions I can set my margins. Let's say I put my margins as 10, 10, 10, 10 on all the 4 directions. Right, I can set my margins so that the labels are not getting cut off. Now once I have put the margins, let me see if I am able to plot the details quite comfortably. Okay, it looks too small a size now because the margins are looking too small. So it's on the 4 directions, it is leaving that much of margins. But what I really want is only from one side the margin should be slightly adjusted. So I can play around with the stuff, right? Saying how much margins needs to be adjusted on what side. Right, so probably if I say the same thing, if I go with 5, 5, 5, 5, slightly the graph gets improvised, but it is getting cut. So the second one I should set it, right? So the second one, let me set it to 10. because this is 1, this is 2, this is 3, this is 4. The second one, let me set it. I think that should solve the problem. Yeah. The second one is being set so that this comes out here. So we get all the values, right? The first one I can set it simple. Third one I can reduce. Fourth one I can reduce the margin as well. So probably instead of 5, the fourth one, let me make it 2 so that it gets slightly more expanded. So this kind of a graph, right? So I can set the margins at each of the stages. I could see that in case of segment urban hip, the values are much in a different range, whereas in case of the other 3 segments, it is coming out to be more or less 5. So that is how I can visualize the confidence intervals across the groups. Multicom package is a real good package which is providing the visual comparisons across the groups. Right, I can assign a AOV object to it and I can inspect it with GLHT. So we have done this exercise, right? We have removed the -1. We have added -1 means the intercept is removed from the model formula, and that model is typically plotted with the way margins also adjusted wherever required. Then the other aspect in ANOVA that I am looking at here is a stepwise modeling process. So now that there are multiple variables, if I want to give multiple variables, I can build models more and more iteratively, adding and removing the variables. So instead of just having a segment, I can try all of them one by one. So this is what I am calling as adding the variables. Either it could start with nothing and it keeps going on by adding one kind of variable, or it starts with all the variables, knocking out one by one, and finally builds up the complete model. So we can use a step, right? Step of a particular model. It tests the model one at a time, changes the variables, so either adds or deletes. Forward procedure keeps adding the variables, backward procedure keeps knocking off the variables. And AIC, Akaike information criteria, is typically being used to compare the models on an overall basis, right? So let's look at using this particular function to see how it works. So I'll take it as step. I'll perform a step. Where I'm taking the AOV between the income versus all the other variables. When I have to say all the other variables, I can put a simple dot. Then income is being considered along with all the other variables. And the data that I am considering is cust underscore segment. This is a simple step function. So this is how it has progressed. You see all of them are going at. So there is the income where I am looking at age, gender, kids, own home. Initially the Akaike information criteria is 5779. We have given all these variables. These are all the variables that are there, right? Because we started off with everything. So slowly you could see here the information criteria has come down slightly, right? Wherein one variable got removed, age, gender, kids, own home, subscribe segment. But the moment it came here, age was removed, gender, kids, own home, subscribe segment. The AIC has come down to this much. Then again now the gender, kids, subscribe segment, own home is being removed now. So whichever is not contributing the best is the worst contributing, that would be removed out of the rest. So you could see here, in which case if I remove the age, the AIC is coming out to be this much. if I remove the own home, the AIC is this much. You could see that overall the AIC is the least in this case, so that's where age got removed. Now again, out of this, if I remove own home, this is the AIC. So if you look at all these cases, this is the case where the AIC is getting very lesser. So own home is removed. Now the same logic here. If I remove one more kids, the AIC is coming the least. So the kids is removed. Gender subscribe segment, I remove the subscribe, the AIC is coming to this. Gender and segment, if I remove the gender, AIC is coming out to be this. And the segment is not getting removed anymore, because if I remove the segment, the AIC is increasing rather than decreasing. So obviously the segment is still there, so which means the segment alone is, so the final thing that is going ahead is income with respect to the segment. So that is how I can very well use the step function to really decide which is the most influential variable across the dependent variable. So when I'm using a dot, I'm using all the variables, but within the dot, if I simply take the square of the dot, then even the interaction effects also will be brought out. You could see so many. So you'll get all kinds of interaction effects, and step by step everything will be removed. So it starts with age, kids, each one, and their interaction effects as well. So all of them will be typically considered. So this is how the model starts: age, gender, kids, all of them, and it keeps removing one by one as long as the AIC is coming down, and overall it narrows down. Even in this case, it has narrowed down on the similar kind of a scenario. Yes, so it was able to come out with income, age, gender, kids, segment, age and gender interaction, gender and kids interaction, gender and segment interaction. So that's the kind of model that has been worked out. We have to be very careful when we are using the squared kind of function, but squared will bring in even the two-way interactions as well. We have to use all this with caution, because one, the positive side is it can really help us with model exploration. But compared to this, we'll see at a later point, the variable selection is becoming more and more comfortable when we are using procedures like lasso or random forest kind of stuff, compared to the using this kind of ANOVA scenarios, stepwise ANOVA kind of stuff, right? So that is what I wanted to look at as a part of this session. So I wanted to test the group frequencies using a chi-square test, which we have done. We have done a binomial test to observe the proportions across the groups. We looked at group means by using a t-test, and we have used ANOVA to compare the means across the multiple groups. If you have any further queries regarding the same, you can very well get in touch with me by giving me a call on the number that I have given below, or you can even send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.